Welcome to the Foundation Lectures on NST. My name is Herwig Mannaert, and in this second part we derive and interpret design theorems which are required to obtain software without dynamic instabilities. Now, we have seen in the first part that we can treat a design cycle and also a software design cycle as a dynamic system. And in order to do so, we have to consider and define an explicit transformation from functional requirements to the construction primitives of software, and treat this transformation as a dynamic system where you have requirements X, where you have software versions of software modules Y, and where you have also a feedback cycle. And the essence of that positive feedback cycle, which may cause instabilities, is the fact that if requirements imply changes to the software modules, ripple effects will lead to more and other changes in those software modules. And in evolving information systems, of course, these changes can be applied, they are applied on a regular basis. It's basically a discrete dynamic system, and they do cause ripple effects. Now, if we represent that transformation, we have on the left-hand side the requirements, which are very basic conceptual requirements, where you need to represent data entities like orders and invoices, and where you need to be able to perform actions, creating invoices, processing orders, sending invoices, and so on. Now, these conceptual entities are transformed into software constructs or modules, data structures or classes containing data attributes, and action functions or classes with a method that actually perform an action. And if we visualize this transformation like this, we also see the actual feedback, the positive feedback causing instabilities. If we have another additional requirement, like an additional attribute for the order, for instance, it's normal that we have a new version, a modification to a version of the software module or construct order, but the dynamic instabilities are caused by positive feedback, being that changes to, for instance, the order data structure will lead to more changes rippling through into other functions and other software modules. Now, in this part we derive design theorems to ensure that we don't have these dynamic instabilities, to ensure that these ripple effects, this rippling of changes, are depleted or damped. And we call these ripple effects combinatorial effects because they correspond to combinations of multiple changes, and we ask that there are no dynamic instabilities, and by asking that we derive some principles which will turn out to be in line with existing heuristics. Of course, these principles are derived based from reductio ad absurdum, and so they are necessary, not necessarily sufficient to obtain system stability. Now, the first principle is widely known, has been known for a long time, is separation of concerns. Suppose you have various tasks that you need to perform. For instance, let's say you collect information of an IoT sensor and you want to represent it in a visual environment on a screen. Now, because you need to do them together at a certain point of time, it would not be unlogical in the first phase to code them, to implement them as two tasks in one single software function or class with a main method. And so these two different things, conceptually different things, would be combined in one single software module. Now, of course, after a while, it would be possible that you would have multiple versions of one of the two tasks. For instance, if you collect data from an IoT sensor, you have another kind of sensor with another protocol, another version of a protocol, so you get different versions of the actual task collecting the information. But however, if you have not separated both tasks, the visualization and the collection of information, the only thing you would be able to do is to duplicate both and change part of the implementation. So you would have various implementations with the same visualization, but another kind of protocol collecting the data from an IoT sensor. Now, when you would then have, at a certain point in time, the need to change the visualization, that visualization would have been duplicated, and changing that would lead to a duplication of these changes. And this is clearly a ripple effect, a combinatorial effect proportional to the size of the system. It is a positive feedback proportional to the size of the system and therefore an instability. And therefore, based on this reductio ad absurdum, we have to separate all the concerns, all the change drivers, all the things that can change independently in separate constructs. Because if we would do that and implement them in separate constructs, we would have a different construct for the visualization and for the collecting of the information through some IoT sensor. And if we then would have afterwards multiple versions of IoT sensors and multiple versions of protocols of IoT sensor, we would simply have other implementations to deal with those sensors. And if then it would be required to have another visualization method, another graphical method to visualize the data, we would only have to change this once and use this changed or modified module to visualize with all the various existing modules for the IoT sensor data collection. Now, separation of concerns is something which has been known for 60 years at least, but however, we state it a little bit more explicitly and say, well, we can only have a single task, a single change driver in an action software module. And there are many manifestations of separation of concerns. The fact that we tend to separate the various tiers in multi-tier architectures, or to externalize the workflow, to separate the cross-cutting concerns like the action-oriented people say, or to use messaging or service buses. These are all manifestations of separation of concerns, separating various concerns or change drivers. If you look, for instance, at the integration bus, you see a clear pattern where there's a combinatorial effect on the left-hand side and not on the right-hand side. Because if you would add another module in a peer-to-peer architecture on the left-hand side, it would mean you would have to implement 8 new connections to the 8 existing modules. If you would add only a module at the right-hand side, you would only have to implement a single connection to the unified bus. So it's not just the number of connections, which is n times n minus 1 divided by 2 at the left-hand side and n right, but it's the additional or marginal effort in adding a component to the bus, which is proportional to the size of the system at the left-hand side and therefore unstable, and which is not proportional to the size of the system at the right-hand side. Why this is an example of separation of concerns? Because at the left-hand side, every connection between two components is dependent on two components. On the right-hand side, every connection to the bus is only aware of one component of a single change driver, because the bus is not considered to be a change driver. Of course, when you would change the bus, this would not be the case anymore. What we also see is that the effort of going from the left to the right is always just a little bit larger than remaining on the left. Though once we are on the right-hand side, the effort drops dramatically for every additional component. As long as you're on the left-hand side, it's always a tiny little bit more effort to go to the right-hand side and do it well, instead of staying in the misery of the left-hand side. There are some implications. We should identify change drivers up front. If we know it's a change driver, we have to separate it. If we don't know it's a change driver, if later on something emerges as a separate change driver, a symbol logging statement, a file rename statement, which suddenly turns out in need to be changed everywhere, then at that point in time, this change driver emerges, and at that point in time, we have to separate it and go, like in the schematic drawing of the bus, from the left-hand side to the right-hand side to ensure that when it happens the next time, we won't have that huge effort anymore. Second design theorem is what we call action version transparency, and we once again start from a reductio ad absurdum. Suppose we have a number of tasks and actions implemented in software, in functions implementing the task, and suppose these tasks or actions, they are dependent on one another. For instance, task 1 calls or invokes task 0, task 2 as well, 3 as well, 4 as well. Now, this is on the left, or requirement or logical representation. If you look in the software, these invocations exist as well, but they also mean there is a piece of software within these calling entities or calling functions that is dependent on the function that is actually called, or the method which is actually called. Now, this means if we would change the implementation, we ask it on the left-hand side, and so we change the implementation of that function that we call, which may be a logger or a data collection or whatever. If the interface is not properly encapsulated, if it is not a version transparent interface and the interface changes, this would mean that we would have to change all the pieces of software calling this function within the other software modules. And it is, of course, clearly a positive feedback effect. This is clearly a combinatorial effect proportional to the size of the system. The larger the system, the more modules will call certain basic modules, and therefore it's a seed of instability, and it's something we cannot have. Now, on the other hand, as you see here, by the way, which is the representation of all the software modules or functions that have to be changed and which are proportional to the size of the system. On the other hand, if you would have the same situation, but at the point in time where you need to have another version, another implementation of your task 0, and you would have a stable interface, a version transparent interface, there would be no need to change software in the calling modules. Now, there are many manifestations as well. It's also well known. Action entities, they need to exhibit version transparency, stable interfaces, not just at high-level business functionality, but basically throughout the fabric of your entire modular structure of the software. And there are many manifestations. Polymorphism is a way of doing that. The use of, in a pre-objected oriented era of wrapper functions is a way of doing that. The interface definition languages, which were specified at the time of Corba, for instance, is a way of doing that, and also service interfaces like SOAP and REST is a way of doing that. But it's not about the technology, it's about the way of doing it, because there were, of course, many ways of doing it 50, 60 years ago. You don't need the latest technology to ensure that you have stable interfaces. There are also some implications. It's not just about having version transparent interfaces on your high-level business interfaces. You should have them at all processing actions, all processing functions and methods throughout the fabric of your modular structure. And you should also very decently encapsulate external utility functions like logging, because everybody knows if a logging interface changes, you have many lines of code in many modules that you would have to change. So basically, if we already look at those two first design theorems, it's about removing the intramodular coupling, removing things that do not belong together, which are confined in the same module and therefore create coupling, removing this module coupling within the modules without introducing coupling between the modules. And so if you have an emerging concern, like a logging statement, a file rename, which suddenly emerges to be a change driver, what you then have to do, of course, is that if you see this as a change driver, you have to create a new task, conceptually, implement it in a separate module, and then all other modules become dependent on that separate module, but because you have a proper encapsulation, a proper stable interface, that call into that new module ceases to be a change driver for the calling modules, and so you don't have any more a problem with combinatorial effects. A third design theorem is what we call data version transparency. And once again, we start from reductio ad absurdum. Now, suppose you have a number of actions, number of action entities implemented in functions or classes with main methods. But these action entities, they pass data between each other. So, for instance, if task 2 calls task 1, but they pass to each other a piece of data, so then they become dependent on these pieces of data as well. And if you look in the software module implementation on the right-hand side, the pieces of software, the lines of code that need to pass that data, they become dependent on that data because they need to create that data, instantiate that data, pass that data. So there are little pieces of software becoming dependent on that data structure or data class. Now, if you would change that data structure by adding, for instance, an attribute, and this data structure would not provide or exhibit version transparency, and for instance, a constructor would have a new and changed signature, then all these pieces of code handling, instantiating, creating, passing that data structure would need to be changed. And that is clearly an instability, a positive feedback effect, a ripple, where the effect is proportional to the size of the system, because the larger your system gets, the more modules will interact with and pass that piece of data, and the more modules will be affected by this ripple, and the instability will grow. So, of course, you can represent it again in a mathematical format, where the fact that you change the actual data structure is, of course, not an instability, but the ripple effects are. How to solve it? Well, once again, it's basically very simple. You have all these tasks which are implemented in software modules. You have this data entity which is implemented in a data structure or class. All the various software modules become dependent on that data structure if they interact with it. So if you change that data structure, but you do a proper encapsulation, for instance, with the default constructors, getters and setters, a proper encapsulation, there is no need upfront to change the various modules or functions that actually call, instantiate, and interact with that data structure. So data entities received produced by actions need to exhibit version transparent interfaces. Once again, this is not new. This has been done for a long time, although not systematically. You don't need extremely recent technologies like web services, REST interfaces, XML. You can do it even with legacy systems, and the very old COBOL systems often used tag value pairs, which were perfectly obeying this data version transparency design theorem or principle. Of course, there are some implications. You should properly encapsulate, wrap all your data structures and classes, and it is very interesting to see in the historic discussions between data coupling and stamp coupling, where there were always disagreements what people should do, whether it's actually stamp coupling you should prefer and not data coupling. You should pass encapsulated references to data objects. The fourth and final design theorem, separation of state, we also start from reductio ad absurdum. Suppose we have a task, implemented of course in a function or class and method, and we have other classes, tasks calling them, invoking them or calling them. Now once again, if a action invokes another action entity, so the piece of software, a couple of lines within those action entities become dependent on the function, action function they invoke. Now, if you change the implementation of task 0 and you encapsulate it well and the interface doesn't change, there is still a possibility that you could have some kind of new exception. Because it's not in software just about invoking the interface, it's also about returning from the function and returning maybe with a possible error state or exception. For instance, you have, let's say, a list of product codes which is in a file available, and then at a certain point of time you change the implementation of the product codes to a central server, and then you can have a completely new type of error or exception where you cannot access the product code because the network is down. Now that's a new kind of exception, and so if you don't store the state, that would mean that if you would have to react to this new type of exception, the only way you could do that, the only place where you could do that is in the invoking code upon return of the error. And so this would clearly, if you would not store the state, would clearly be a combinatorial effect, a dynamic instability, a positive feedback, because it would be proportional to the system. The more the system grows, the more modules will invoke a certain action function, and the more modules will need to be changed in order to cope with a new error or exception. Now, we can represent this as well in terms of the collection or sets of the action functions. Now, how to solve this? Once again, quite easy. What we need to do is that if we call this and we have a new kind of exception, yes, that we simply store the state and do nothing else, and if new types of exceptions or possible errors emerge over time, well, new types of error states emerge in that central single store, and some other action entity or function could try to cope with it and take appropriate action. Well, also manifestations of this state-keeping mechanism are abundant. We have lots of asynchronous communication systems trying to store state. We have stateful work systems. A lot of people, they say you should have a synchronous processing, which is far more reliable than synchronous possible processing. We have CI/CD build pipelines, etc. And one of the things, the coding implications say so that we should make workflow systems stable, isolate actions, expose transaction states. Be also careful with automation dependencies like Maven, project object models, where you can, drag in and drag in and drag in and drag in various dependencies in an open way. And so I would here try to give a brief explanation of the dangers from that point of view of synchronous object pipelines. Now, suppose that you have an assembly line where people work on a car. Now, people often compare this to an object pipeline in object-oriented programming. But that's not the case. If you have an object and it invokes another object, it does so after it has executed some lines of code, and then the next one executes some lines of code, the next one, etc., etc. So what basically happens is, if you would have an assembly line of a car, you would add, for instance, a door to the car, and then a window, and then a handle, and then paint the door. But what happens in the object-oriented pipeline at the lower end of the drawing is that you would start adding the door but not finish it, then would start adding the window but not finish it, then you would start adding the handle but not finish it, then you would paint the door, then you would finish adding the handle, then finish adding the window, and then finish adding the door, which is not decoupled, of course, because they tend to be in an open model and they tend to be waiting for each other dependent. And if you then would have an error, for instance here, you could know for sure whether that error comes from something which went wrong in the upper part of this second function, or something which went wrong in the lower part of the third function, or something which went wrong in the fourth function. Because they're waiting for another. They are coupled, not in an invocation way, but they are coupled in a runtime way. They have to wait for each other dependent on timeout, on memory things, etc. So separation of states theorem asks for stateful workflow and not these asynchronous object pipelines, which are far more dependent and coupled than an assembly line. But so if you would do that and say just, okay, I call the first function, come back the second, the third, and so on, you would have far more decoupling, and you would know that the first function has executed successfully and the second not. You would know that the second would take too long, for instance. You would know there would be a memory problem after the second function, etc. So you would have far more decoupling in such a way. The same with async processing. Async processing is often much more reliable, but of course you should take care for this example of a callback hell, where you have inline callback functions which can create quite a mental gap between the code you are looking at and what happens at the runtime of the software. Now, looking back to these design theorems, we see that fundamentally what they are saying is that modular structures, architectures combined with changes will lead to combinatorial effects if you're not careful. These are the basic feedback mechanism that we have explained due to rippling of changes. And this rippling of changes is caused by hidden coupling or dependencies in the system. They are proportional to the size of the system, to the growing size of the system, therefore will become unbounded and therefore are unstable from a dynamic systems perspective. And actually they emerge and appear at very basic orthogonal levels where you basically combine some actions, some data, pass some data, etc. We also see that these design theorems are completely aligned with current heuristic knowledge, which is a good thing. However, they unify to some extent. Instead of tens and tens of heuristic rules or bad code smell rules, there are only 4 design theorems which really explain most of these heuristic rules and these bad code smells. They also explain them based on a causal reasoning, all based on the fact that combinatorial effects, positive feedback mechanisms, changes ripple through, and that what you don't want. So you can explain nearly all heuristic software rules, design rules, based on the fact that you want to avoid, dampen, deplete combinatorial effects. And they also clarify or elucidate some underlying concepts, because when you prove something, like separation of concerns, you need to state in an unambiguous way what a concern is. And it's not just something we have to deal with, it is something which can change independently, a change driver. If you look again at the double dictum of Dave Parnas, low coupling, high cohesion, well, these remain, of course. We still say low coupling, high cohesion remain. However, we say low coupling is low coupling between the modules, data version transparency, action version transparency, separation of states, and high cohesion is actually also some kind of coupling. It's low coupling within the module. If you combine things within the same module, they are confined and therefore coupled in some way. And separation of concerns, separation of states hints and points to high cohesion. However, we clearly say coupling and cohesion are basically the same. High cohesion is a way of low coupling within the modules, and they are a bit refined. It's not just about counting arrows in coupling, because if you would have a logger which you use everywhere, you would have many dependencies to that logger. But that's called reuse. You shouldn't use 100,000 different loggers to avoid 100,000 dependencies on the logger. However, that logger should not change its interface, because then you have ripple effects. So it's not just about counting arrows in looking at coupling between modules. It is about the propagation of the ripple effects. So if we summarize that, then we say that basically these design theorems, and therefore most heuristic software knowledge, are about coupling, and more specifically the avoidance of ripple effects. We need low intramodular coupling, low coupling within the modules, which is known as high cohesion. And we need low intermodular coupling, coupling between the modules, which is known as low coupling. And coupling is not just about counting arrows, it's about the nature of the connection. It's about whether ripple effects pass through or not. If lots of modules use the same underlying module, that's also caused reuse. That's not bad on itself. It's, however, about the nature of the connection. If the ripple effects pass through, that's bad coupling. And cohesion is not just about splitting into a sea of modules. We also need to consider the hierarchical aggregation of related modules, but we will come back to that in the next part. So, of course, if you have any remarks or questions, you can always contact me, and thank you.